Good afternoon, I am Jinhong. The topic of my presentation is design considerations for broadband performance of 2 degree of freedom nonlinear vibration energy harvesters. I would like to introduce first what 2DOF MCBH is. Figure A on the left side is 1DOF case. There is a cantilever beam and a permanent magnet is attached at the tip of it. And the beam is a piezoelectric bimorph beam. As shown in the figure, the metal shim is sandwiched by the piezoelectric composite material. And the external load resistance is connected to the piezoelectric part. When the device is subjected to an external harmonic vibration, the beam oscillates and the voltage is generated across the load resistance. For the 2DOF case on the right side, there are two beams. Now the magnet on the right side can also oscillate and two beams generate voltage outputs. The important thing is the position-dependent nonlinearity is imposed by the magnetic coupling. According to the magnetic field, two types of systems can be defined. First one is a monostable system, and the second one is bistable system. In the bistable system, there are two static equilibrium positions, left and right, and the oscillation C is desirable for its large amplitude. This large amplitude oscillation C is called interval oscillation. In the presentation, I'm going to focus on the 2DOF bistable case. This harvester is abbreviated to 2DOF MCBH, which means magnetically coupled bistable energy harvester. If the system is mathematically modeled, then the oscillator model is obtained as follows. Please note that only the magnetic coupling force is nonlinear, and finally, Duffing-type nonlinear oscillator is found. In design process, it was found that in the first primary resonance, harmonic distortion should be considered. I would like to suggest an evidence for it. The first row shows the 1DOF case, while the second row shows 2DOF case. For the 1DOF case, phase plane response, time response, and FFT result demonstrate the high-order harmonics are almost negligible. However, for the 2DOF case in the second row, it is interesting that especially beam 2 shows a significant third harmonic component relative to the fundamental harmonic, as shown in the FFT result. If harmonic balance analysis is conducted, the importance of harmonic distortion looks obvious. Figure A shows frequency response of beam 1 in the first primary resonance. The green one is the interval oscillation, and its harmonic balance results are shown in B. Herein, capital H means the truncation order of harmonic balance. Because for beam 1, distortion component was minor, the first order truncated solution is roughly similar to the third order truncated solution. However, for beam 2, harmonic distortion plays a significant role. As shown in D, first order truncated solution look very wrong compared to the higher order truncated solution. In this case, the third harmonic distortion and fifth harmonic distortion are plotted in A and B respectively. These demonstrate that harmonic distortions are significant for beam 2. If RMS voltage output of beam 2 is calculated at the point with the asterisk in B, figure C shows that the estimation decreases as the excitation intensity increases. However, if the third harmonic distortion is considered, voltage output is proportional to the excitation force as shown in figure D. Please note that this tendency is different from C. Moreover, if the fifth harmonic distortion is additionally counted, it is found that the voltage output is larger. Thus, it is stated that for beam 2, high order harmonics must be considered at least up to third order. Conventionally, in order to maximize the power output, the external load resistance has been optimized by using the impedance matching technique. This matching technique is based on the first order harmonic solution. However, as demonstrated previously, the high order harmonics were significant for harvesting performance. In this regard, we optimized the load resistance considering the third harmonic distortion analytically. As a result, we obtained the following polynomial equation for optimization. In the graph, our opt1 and our mat1 indicate the optimized resistance and the matched resistance of beam 1 respectively. Because the fundamental harmonic was dominant for beam 1, the difference between two curves is indistinguishable. In contrast, for beam 2, the difference is significant. Finally, those figures show the improvements of RMS power output by the previous optimization process. For beam 1, conventional impedance matching technique is effective because the red and blue curves are almost the same. However, for beam 2, if the optimization is performed with third harmonic distortion, the RMS power output is remarkably improved. Please note that the green curves are plotted to show the case without any optimization technique. For nonlinear energy harvesters, broadband performance is the most important. To evaluate this performance, average RMS power is estimated numerically. The magenta triangle indicates the maximum point, which is numerically obtained. The red star indicates the optimization with the third harmonic distortion. In this case, the resistance is optimized near the saddle node bifurcation point on the right side. The blue square indicates the result with the conventional matching technique. Figure A shows for beam 1 the conventional matching as well as the newly found optimization. Both are quite excellent because the star and square are close to the triangle. For beam 2, however, the conventional matching technique provides a poor broadband performance. On the other hand, the newly suggested optimization shows an excellent result. When both two beams are considered, the tendency is the same as shown in figure C. Finally, the conclusions are following for designing two DOF MCBHs. First, the two DOF MCBH showed complicated dynamics compared to one DOF case. Second, especially beam 2 yielded harmonic distortion components. Third, load resistance should be optimized by considering harmonic distortion. And the last is newly suggested method successfully optimized the broadband performance. Thank you for your listening.